Okay, hello everyone. I'm Alina Lazar, professor in the Department of Computer Science and Information Systems at Youngstown State University. And I'm going to present the paper GPU-based classification for wireless intrusion detection. This is a collaboration with Alex Sim and John Wu from Lawrence Berkeley National Lab. So with the growth of 5G wireless technologies and IoT, it becomes urgent to develop robust network security systems, such as intrusion detection systems. These systems need to detect unauthorized access and attacks in real time. However, in order to automate this, we need to build complex machine learning models that usually take a long time to train and update. So the proposed work shows how to implement machine learning algorithms using the Rapids AI QML library that can be done, that can run on graphical processing units, GPUs, in order to speed up the training process on large-scale data sets and while reduce the training time, but in the same time still being able to provide high accuracy and performance. So today, smaller and smaller sensors and wireless devices interconnecting through the internet can be found everywhere. However, cyber attacks are threatening everything these days: banking, shopping, other digital services. So due to the increase of cyber attacks, intrusion detection systems are vital, and they must become an integral part of any network anomaly detection systems. Network providers should tune and continuously monitor their hardware and software to guarantee reliable, high quality, and uninterrupted services. So previously, extensive research has been conducted on building such systems. However, cyber attacks are becoming more and more sophisticated, and security experts see machine learning as a promising technology to help identify such cyber attacks. So machine learning can provide accurate, efficient, and automated approaches to detect intrusions and attacks. Now, even if machine learning methods have proven before that they can detect attacks, the mechanics behind it is not very well known. So in order to build such performant machine learning models, you usually require large data sets of labeled instances that are usually not available, and it's time consuming and expensive to create such data sets. So to detect intrusion detections in network transfers using machine learning models, we need to have like records of normal and intrusive data. in order to be able to train these machine learning models. For our research, we are using a well-known dataset publicly available called AWID, which is available since 2015. And the focus of this research is to find if to discriminate between normal and attacks. However, in this data set, the attacks include 3 different types: impersonation, flooding, and injection. So the current problem is that the network is only checked when there is something wrong with it. Machine learning models can provide a way to automate this process. However, in order to build these models, we need existing data sets. And given the fact that networks are dynamic systems, these machine learning models have to be continuously updated in order to be able to deal with new types of attacks. The volume size of the data has a direct impact on the training time. So, which means that very large data sets may become unfeasible to train if you don't apply any scalable strategies. So for this reason, we present in this work a study exploring large-scale implementation of classification algorithms available for the GPU through the data science library named Rapids AI, especially with the next generation of exascale computing that will combine CPUs and GPUs. This is becoming very important. So this Rapids AI package provides efficient implementation of many multiple classification algorithms. And by using these, we are able to train multiple classification algorithms, and these provide up to 65 speed up over CPU implementations. In terms of previous work, so the AW dataset is from this paper published in 2015, when Collias and his co-authors collected a set of wireless intrusion detection data sets and made it publicly available. This data set was collected in a small office simulated environment. They perform 16 different types of attacks, mainly categorized in 4 main classes. And when other people use this data set, so the data set was used to run random forest algorithms before, and the only paper that uses a GPU related approach was an XGBoost algorithm. However, in that paper, only 125,000 instances were used, but the paper doesn't provide any timing comparisons or performance As I mentioned, we used around 6 different classification algorithms and ran CPU and GPU implementations. 3 out of the 6 algorithms were tree-based methods, and I'm going to start with random forest. So random forest is a tree-based algorithm. It works very well with imbalanced data sets, large number of features. It can handle categorical features and missing values. And one of the advantages is that it doesn't require a long training time. And it also provides feature ranking and selection. The other two tree-boost algorithms, XGBoost and CatBoost, offer just additional improvements over the random forest. Because so for example, XGBoost has built-in cross-validation and automatically deals with missing values. And then CatBoost has the capability of automatically converting categorical features. So you don't have to do a lot of pre-processing. For benchmarking or like baseline classification, we use the multinomial naive Bayes, which is just a simple probabilistic classifier. Also k-nearest neighbor, which just using majority voting, and also support vector classification. Now in this table, you can see some upper bound complexity of these machine algorithms. Support vector classification is the one that has the most computational expensive training time, and that can be seen at the results at the end. So the data set we used is called the Eigen Wi-Fi intrusion detection. Is a popular publicly available collection of data sets. We have a large one and training and testing, and a reduced one. The tabular data set includes 154 features. These are from different 4 classes, normal and 3 different type of attacks. The features mainly store MAC layer information collected through Wireshark. So for this project, we used a combination of some of the data sets available in this collection. So I combined like 2 or 3 smaller data sets into a larger one that has over 8 million network transfers. The ratio between the number of normal and attacks is like 14:1. And then actually, I haven't used all these for training. The training data set was set at around 4 million instances. So before applying any algorithms or building any models, data processing was done. There are multiple features with different data types and value ranges. So some of the MAC addresses had to be converted from hexadecimals to integers. The training data set has many missing values, so we converted this to zeros or like eliminated some of the features that do not have enough values. And at the end, just before running machine learning algorithms, all the features are normalized using the min-max scaling procedure. So in terms of experiments, the experiments were performed on the computing nodes at the Whitespace Computing Center. These computing nodes have 48 CPUs, 384 gigabytes of memory, and two GPUs. So they have GPUs with 32 gigabytes of memory. We use the Rapids 0.18 Conda environment with QDF and QML. And we ran all these machine learning algorithms, naive Bayes, scan, and support vector classification, random forest, XGBoost, and CatBoost. So we run like experiments in a loop with different training data sizes. First, the data was divided into training and testing. Scaling was applied to both data sets, trained the model, and in the end, the prediction was done to evaluate the model, get the accuracy, and record how long it takes to train. So we ran these experiments on CPU and on GPU. You can see in these tables a comparison in terms of accuracy for all the algorithms. It looks like support vector classification, XGBoost, and CatBoost performed the best. They just give 100% accuracy and precision recall F1. While random forest still gives good accuracy, but not such good precision and recall. So these figures here show the training performance comparison between running scikit-learn on the CPU on the left and the GPU on the right for while training a data set of 4 million instances. So we can see here, we could not even run support vector classification with more than 100,000 instances. Then on the CPU, CatBoost and XGBoost take less than 20 seconds, while random forest takes like around 60 seconds. This is much less on the GPU, where CatBoost, random forest, and nearest neighbor take less than 3 seconds, while XGBoost runs in about 7 seconds. So in just like putting this all together, the most improvement can be seen for random forest, which runs 65 times faster on the GPU. And for CatBoost and XGBoost, it's like between 2 and 5. This is probably because CatBoost and XGBoost are already tuned, and they are actually optimized implementation over the random forest. So in conclusion, we are presenting a scalable machine learning workflow to speed up network intrusion detection, classification over large 5G data sets. So we can see that the speed up goes up to 65. The pipeline can be definitely adapted for other intrusion detection data sets. And in future, we can extend this to run it on multiple GPUs using the Dusk library in order to run training with even a larger data set. And also, we can try to apply the same approach to other data sets and maybe compare the classification algorithms here with deep learning. So this research was supported by DOE, and also we use resources from the Ohio Supercomputing Center and NERSC. And thank you for listening, and anyone has any questions?
Questions, please.
Have you looked at the cost of the GPU instances versus the performance?
You mean like how much money?
Mm-hmm.
So not for this particular one, but I look into that for a different application, and usually it's 5 times cheaper to run it on the GPU.
5 times cheaper? Okay.
Especially when you have like large problems that require lots of CPU cores. With the prices at Ohio Supercomputing Center, it was like 5 times cheaper.
Because it was running so much faster,
right?
That you didn't have to run it for long. Mm-hmm.
Yeah, but you need to have something that's implemented like in CUDA on the GPU to be able to get that type of like, yeah.
But your the toolkit that you use for all the ML, this P something, that already had implementation for CUDA, and you didn't have to deal with implementing the
yes. So Rapids AI is like C++ library that you can use in Python to run all these machine learning algorithms. So.
Okay. That's great. Thank you.
Any other questions?
I have a question. For the accuracy between CPU versus GPU, did you apply feature reduction for both, or just like GPU only?
Yeah, I just used the same data set to.
Same data set.
Yes. To run it on both.
Yeah, but the accuracy shows like a little different results when you use CPU versus
right, because so the algorithms, the implementation, even if it's the same algorithm, the implementation is different, right? Because on the CPU I was using the scikit-learn, and on the GPU is this Rapids AI, so they have like a slightly different implementation.
Okay, makes sense. Okay.
That's why.
Okay. Any other questions? Okay. Thank you, Alina. And let's move to the next paper. Next paper is from ESnet. So I believe Richard Cziva, you're gonna present, right? Okay. Please go ahead.
Yeah, thank you. So I'm going to present you this short paper. This is a bit more practical. We didn't use machine learning or GPUs or CPUs at this point, although we are trying to also do similar type of classification on the data that comes out from the system. But this is going to be, this talk is going to be about how we implemented the telemetry collection software, essentially. So here are the authors. Zhang Liu was an intern at ESnet, and he's been working on this quite a lot. The others are Yatish, Bruce Chin, staff members at ESnet, and I'm Richard Cziva, and I'm a data science engineer at ESnet. So for those who don't know, we are essentially a network service provider for DOE labs and supercomputers experiments. But I think given the participant list, this is pretty evident. So for this project, the motivation is that we have, and all network providers have, an increased need for programmability, and this means that given we are transferring more and more data, we also would like to have better visibility to what data are we carrying. How can we handle, for example, application-specific traffic? And in general, how can we introduce programmable services into our network to benefit our operations or monitoring, as well as how can we provide these new programmable services to our users? Let's say an LHC experiment. So if you think about monitoring and you think about SNMP or NetFlow as the two big players. Now, in both of those, they are sampled and aggregated. That means you don't have very fine-grained visibility into your network. But with our new solution, which is called high-touch services, we are building out a per-packet telemetry system in ESnet. Now, the way it works is that we're using these servers, the very high-end servers deployed in all of our points of presence in the network with these FPGAs, which are Xilinx U280 cards that have 200 gig ports and memory on chip and a powerful FPGA to load your program. So coming back to what sources of data you can use for network telemetry, I just want to give a small comparison here just to put high touch into context, or in general, like a per packet telemetry system into context. So with SNMP, you're essentially polling the interfaces every, let's say, 30 seconds. That means your data rates are 130 events per second. In an SNMP scenario, for let's say 4,000 interfaces, that's the amount of interfaces we have. For NetFlow, you're essentially sampling the packets. So we are using 1 to 1,000 sampling. That means like a raw data rate of 6,500 events per second. If you go one step further, per packet telemetry means every single packet of the network will become a telemetry packet. This is where data rates explode, obviously. It can go up to 8 million events per second for a single interface. Of course, it depends on packet size. So the larger the packets, eventually the less amount of packets you have. So you get lower amount of telemetry packets. So this is where we did a small analysis on packet sizes. If you look at this graph, for example, we see that different interfaces have different average packet sizes in our network. But in general, we ran this data collection, and we came up that we'll take average for a science traffic as 1,500 bytes. Even if we have some jumbo frame, even if we have jumbo frame enabled LHC1 interfaces, for example, it's not enough to make every packet jumbo frame. So still today, that's a good estimate for what an average packet size is. And if you take that 1500 byte, you can see that 100 gig link, 1500 byte packets fully utilized will result in 8 million telemetry packets per second. So that's for a single 100 gig interface. If there would be on average jumbo frames, then you would go down to 1 million packets per sec. The system is about to handle around 15 million packets per sec on a single machine. And the overall architecture looks like this. So we have the routers that carry our production traffic. We would mirror out selected interfaces or flows even from the routers to this high-touch server to the FPGA first. The FPGA is the part that will create the actual telemetry packet. So it strips payload. It makes a new IPv6 packet, which is essentially then we call a telemetry packet that is being forwarded to on the same host to a Mellanox 100 gig card. And that card is very popular in DPDK world. So DPDK is the data plane development kit. It's a software toolkit that you can use to read and write packets very quickly using some cards like the Mellanox 100 gig card without touching the kernel. So it's like a kernel bypass technology. And we are using that as well in this project. So FPGA creates the telemetry packets, and then we have this part that has to read this 8, 10 or more million packets per sec to process the data. So we're developing this software called FastKappa NG, which is this DPDK program. It's based on a project that's no deprecated, but it's from Apache Metron called FastKappa. They have initially started like a similar project, but we took it over, made it NG, like next generation. And we are basically the developers of this now. So it uses DPDK. It's fast, as I said, it's a packet processing API, which is very popular now if you want to bypass the kernel. And the whole system is built to handle millions of packets per sec while preserving order, which is one of our biggest challenges in implementation, to make sure that the original order of the packets is retained until they get to, let's say, Kafka, or when they are written into file. When you do some analysis on sequence numbers and of the flow, it's very important that they are not mixed up. There's essentially, you want to, for example, look at the exact order they were on the wire. Bit of technical detail here. The way this works is when the packets come in, you have to put them into different receiver queues on the NIC, and then you use a hashed algorithm called RSS, which does this for you. This has to be tuned to your traffic and to your packets, so your distribution is as uniform as it could be. Then once they are in different queues, this NIC can, let's say, support 8 queues, so you have 8 pipelines. Then you have to read them from with the CPU process here, put them into some rings. And an important part is that if you want to process them in a pair flow way, you'll have to classify them as well. So we are using this ACL worker, which is like a popular building block in the DPDK ecosystem. You can go over all of your small little packets and put them into different rings, per flow rings. And once you have those, then you can process them by flow workers, which are so-called service cores. This is where you can implement your functionality inside the DPDK application. So you can sample the packets here, which means from your input ring, you take 10 packets, but you only emit 1 to the output ring, let's say every 10th packet. or you can create histograms, aggregate the data inside these service cores. And then we have some cores here that just handle the Kafka processing, because eventually our goal was here to get every data into Kafka so our applications can read from Kafka. So the service cores are really beautiful to program in our system. So you eventually have to write it in C, but you get an array of packets when you do DQ from our input ring. And bear in mind, this is per flow. So every single flow will be treated differently. It's already being handled in a previous stages of the pipeline. And then you do some processing here. It's a sampling, so every 10th packet will be then enqueued. And for the packets you don't need anymore, you will free the mbuff and just move on. Packets is dropped at this point, so it's easy to program. And you can configure a lot of things. You can configure what service function to run on what flows. So for some flows you want to run histograms, you can configure that. I didn't mention, but you can match flows on a 5-tuple, like source IP, dest IP, and so on. Or you can use flow ID, which is being generated by the FPGA. So it's a kind of a good thing to offload to the FPGA to track the flows and give a unique identifier for the flow. Because it's quite hard to do, and the FPGA can, if the FPGA already gives you the telemetry packet with the flow ID set, it's easier just to handle that on the DPDK side. We build a lot of monitoring into the system. It's not that interesting, but we essentially know in exact stages of the pipeline where the packets are. We can monitor if there are drops. For example, if the ring fills up, cannot handle more packets, then we'll see. Performance is important. The goal is to handle as much as we can. With Kafka, there's a bottleneck, of course, but this, in order to scale it up, you can run multiple producers. That means FastKappa NG runs multiple CPU cores in parallel to push into Kafka. On a vanilla, unmodified Kafka, you can go up to 5 million packets per sec on a single server with these Docker containers ingest. So 5 million packets per sec into Kafka. At one point, the performance will drop if you want to push more. It depends on the environment, but of course it scales up linearly and then it drops back. And this is just like a basic number to keep in mind. So 5 million packets per sec ingest. We mentioned that for 100 gig interface, we're looking at 8 million packets per sec. So it's not quite there. So you have to do something here. The most obvious thing is that you can put more telemetry packets into one Kafka message and essentially improving your rates of telemetry messages to Kafka. So that's what we did, although this was not desirable because the application that handles the telemetry stream will have to unpack the Kafka messages first and see, let's say, 32 telemetry messages inside. So there's a trade-off, but we had to do it to keep up with our rate. With that, we went up to 15 million packets per sec. This is 50 million telemetry messages per sec into Kafka. And you can see here, the more telemetry packets you put per Kafka message, the better the rate becomes. So we're actually using 32 at the moment. So this will give us the 15 million rate, which is perfectly enough for 100 or even 2 times 100, so 200 gigabit per sec stream at a single server. One more thing before I run out of time, you can do this with Kafka streams. Like this high-level predicates allow you to do like more functional programming approach when you do an application. So here is a small SIM flood. You can filter packets, you can group them, you can window them in this programming language or this context. And we're experimenting with this to do some basic applications. Now, of course, this here does not unpack the message, so it has to be done in a different place. But this looks very promising, and you can run this on scale as well with multiple processing doing the same thing on the stream, which is essentially a Kafka topic. So I presented you first Kappa NG. It's this is DPDK program that we wrote, can push up to 50 million telemetry packet messages to Kafka with a single server. And we are also looking to open source it and just make it available to the community fall 2021. And with that, I'd like to thank you.
Thank you. So if you have any questions, please.
I have a couple of questions. First one is there a sampling for the collected data like NetFlow or SNTA, or does it collect everything?
Everything, it can collect everything.
Okay. Second would be that would the data collection to the remote high-touch servers compete with the actual data flows? It seems like the handling millions of packet messages per second would be accumulated to some amount.
Yes, it was originally the case. We wanted to do the remote, but we haven't tried it yet. But the remote would be that you run the Kafka on the remote server, and you basically just send from the fast Kappa running on locally to a remote. But there's some implications on the network, and we would generate quite a lot of data just by sending the telemetry to a remote one. So we haven't done it yet.
Okay, thank you.
Okay.
I have just a simple question. After collecting the telemetry data, what is the current usage? Like for what kind of purposes mainly?
Yeah, so this is what we're going through every day. We try to find something that's useful with the data for operations or for research. One thing that we've done, and I think it's pretty cool, and is that we analyzed inter-packet times, the gaps between packets. Because I haven't mentioned, but the FPGA can do a nanosecond accurate timestamp. It's a free running clock, so not synchronized, but at one location you'll have the times. And for different TCP congestion control algorithms, if you plot them, the histograms or the different ways to plot the inter-arrival time, you can see different fingerprints or like different ways they look at. Now we did that, and with a machine learning, I think some CNN, I don't remember exactly now, but we managed to classify the flows in terms of their congestion control algorithm just by looking at the per packet data and this kind of very fine-grained timing. It was a lot of data, so the trade-off is how can we aggregate some of, right now we're working on aggregating the data in the FPGA. So instead of sending millions of millions, if we identify in the software that you can do this congestion control algorithm classification and it's important, we'll try to move that piece of code, maybe a simplified version, to the FPGA. So it's being done on the original packet source instead of going through all these hoops to get millions of packets into software and doing it there.
Okay. Thank you. And another question would be like, the KAIDA at UCSD, they're also capturing like traffic from internet backbone, and also ESnet is also doing that kind of thing. I know the ESnet is more focusing on scientific data, but like for example, like public availability, something like that. How would you like to compare your data versus KAIDA data?
Yeah, the KAIDA traffic traces, most people, when they refer to it, is the passive traces that they collected in some Equinix peering points of one network. Actually, they're not collecting that anymore. So the big KAIDA one, I think it ended a couple of years ago. Those are PCAPs and anonymized PCAPs. So as a network provider, we have the luxury to have all the information that matters, the IP addresses, and as well as the timing is what not available from KAIDA, because we have the timestamps in our telemetry packets. And one other thing is that we have it in every single points of presence. So not just a couple of locations, but everywhere where traffic can enter our network. So if we build, the system is really huge, and in terms of investment and manpower now, it's 10 people working on it. But once it's up in operation, we can look at any scientific flow entering the network in 2 points, when it enters and when it exits. And we can do all the analysis and what happened inside of our network. If there are packet loss, we'll see that immediately. Challenges are, it's a lot of data, and it's not that easy to crunch through. And it's live. We're not saving it in PCAPs because it would be an astonishing amount of data. Or we just drop the payload, but even payload dropped, if we would save every telemetry packet, we would create hundreds of gigabytes of PCAPs per location in every couple of minutes.
Right. Okay. Yeah. Thank you.
Thank you.
Any other questions?
Actually, I've got one. So you mentioned that there could be a potential problem related to the scalability of the Kafka server, right? Yes. So is there any drawback in thinking about partitioning the data, splitting the data, and processing through multiple Kafka server? This would require an aggregation steps later on, but could be feasible.
Yeah, I think that's one of the, it's a good way to, I think, to scale up more. We're not using partitioning manually. We are using just the automatic partitioner when the server just figures that out in a round robin fashion. If we could assign the partition in fast kappa ng, we could. Of course, the hard part is you have to be smart with the partitioner there, and some flows are huge and you want them to end up in one partition. There are some smaller flows, you can put them together into one partition. Now figuring that out is not something we've done so far, but it could be next step in the Kafka. Although I would add just one thing, we think we already reached the limits of Kafka, and we're more focusing on how to reuse the data in the FPGA. So I think that's the goal, to push everything to the data plane, everything that's possible, and let the FPGA do it, because that can handle terabits per sec. Drawback is we have 4 FPGA engineers, and even the simplest thing, just to track flow start, flow end, you have to implement some TCP state machine. You have to do quite a lot of work, and for that, with 4 FPGA engineers, it's 6 months. So when we come up, let's classify TCP congestion control this way and that way, you can imagine it could be like years of implementation in Verilog to do that. So the trade-offs are clear here, software versus FPGA.
I see. Thank you.
Thank you.
Okay. Thank you very much for the presentation and also for answering the questions. Thank you.
So I'm Zhang. Thanks, for the introduction. This is joint work with Yumeng Wang from UC Berkeley, Alex Sim from Lawrence Berkeley National Lab, and Shinjae and Shigeki Misawa from Brookhaven National Lab. The bottom of the image is a view from Lawrence Berkeley National Lab. So you are welcome to visit us when everything is opened up. And it's a great view of UC Berkeley campus, the UC Camp Lily in front of the Golden Gate Bridge there. So I'll have just about 4 parts in this. So I'll start with a short introduction with this presentation. So to start with, where are we doing this, or where do we get the data for this scientific data accesses? And this particular set of data is from the tiered storage system of a large high-energy physics experiment. The experiment is run out of CERN, and this map shows two tiers of the storage, top 2 tiers of the storage. Tier 0, where they get everything, where the experiment is actually run, where they have more than 350 petabytes of data. You can imagine much of that is on tape. And we'll be focusing on a particular site in the US. This is a site at Brookhaven National Lab, and it is the tier 1 site for Atlas experiment. Just in case you might be curious, what is this Atlas experiment? It might be hard to explain since I couldn't understand the details of high energy physics. What I would just mention is these are the guys who discovered the God particle. And if you want a more technical name, the technical name for that is called Higgs boson. So this is an important experiment with lots of data. And just to give you an example, they have 15 petabytes of disk just dedicated to this particular experiment. And the graphics on the lower left corner is showing a diagram of computing facilities. In this diagram, the upper right part is the resources dedicated to Atlas, and it shares the tape storage resource with a number of other facilities at Brookhaven National Lab. So I'm narrowing down to the tape storage system and the disk storage system. So just to reiterate a little bit, Brookhaven National Lab hosts the tier 1 site for this Atlas experiment in the United States. It has about 76 petabytes of data in 80 million files on HPSS. That's the tape system. There is a dedicated 15 petabytes of disk cache that's reserved for Atlas data. And now to go to the next level of detail, this disk cache is managed by a system called dcache. The objective of this study is to study the usage pattern of the HPSS files at Brookhaven National Lab to find opportunities for improving data accesses. For example, because it's a tape file and getting a file out of the tape is dominated by the time to retrieve the tape using the robotic arm, then mount the tape to the disk, to the tape reader, spin up the tape. So if there's a chance that you have 2 or more files to be read from a single tape, it would be much better to combine all those accesses into one tape movement, right? Are there opportunities like that? Can we find it? And there's another example that we could be looking into. For example, the physicists organize their data into groups of files that is also called a data set. Each data set would have some feature that's meaningful to the physicist. For example, the detector or the collider was configured in a particular way to detect a particular type of event. So presumably, if you want to analyze one of those events, you will be analyzing all of the events in a particular data set. So putting the data set on disk would be another way to reduce the movement between tape and disk. So we're looking for this type of opportunities, but that's subject to what we can glean out of the data files. The data files we are looking at are the Dcache log files. For this particular study, we were looking at log files from January of 2019 to March of 2000. During this time period, there are about 5 petabytes of files being accessed. Of course, some of the files are accessed many, many times. And the data that we need to deal with is come to us as compressed CSV files. And there are about 75 gigabytes of those files that we actually need to work with to understand the access logs. Just in case you need to go and don't have time to listen to the rest of the talk, the bottom line of the message is Dcache is working very well. When I'll give 2 specific numbers for this. One is out of 50 requests to Dcache systems, only 1 is about that really needs to go touch the HPSS system. So in other words, the cache hit rate is 98%. So that's a very high cache hit rate. Sounds like, well, maybe there, if the cache hit rate is already 98%, there's not too much room for improvement. But there are 2 things. One is during this more than about 15 months period of time, we are touching only 1/3 of the storage, disk storage space, right? So there's more capacity that is around. And second point to note is for the new files that we do need to go to HPSS to do something. 70% of those files are used multiple times. That means potentially there is room to improve the cache hit rates even further, to reduce the cache missing rates even further. So short messages, Dcache is working well, but there's still opportunity to potentially improve the system. Given that overview, now I'm going to talk just a little bit more about the access statistics. Maybe I should slow down and ask if there are any questions. Okay, continue. File access statistics, right? I mentioned 2%, and here's a typical day. If you look at the median day and the different types of accesses, the store and restore, those touches, well, and ring. There must be something, oh, okay, yeah. Okay, so store and restore are the operations that touches HPSS. The rest of them don't. And you can see there are millions of requests coming each day, and those requests and transfers are operations on disk, and they don't touch tape. So what we see is there are millions of those. There's only tens of thousands of stores and restores altogether. Okay, so that's where we got the number less than 2% from. And overall, the hit rate is more than 98%. from day-to-day variations, what you can see is on some days, the vertical axis is the count of all the different type of accesses, and they're stacked together. What you see is that's 1E7, that's 10 million. So the tallest bar here, that means there are a few days where we have nearly 17 million various type of accesses. So sometimes it's very busy, but the average is about 0.1, or that is 1 million. No, that's 1 million unique file access each day. So one of the things that you might be curious about is, okay, so there on an average day, there's about a million unique files accessed. That's what this right figure is showing. And each dot here represents 1 day, how many unique files are accessed. On the left side is how many total file requests each day. And what we see, it ranges from 10 to the 5th to about 10 to the 7th. So oh, sorry, I guess I got these two numbers swapped. The total number of accesses is about 3.5 million, and the number of unique files is about 1 million. And that's give you the headline number of each file is on average accessed 3.5 times. Sorry, I need to, I'll correct that in a bit. So that's the general file access statistics. What comes next is a set of accesses to tape. The first thing is showing here is a histogram of access speed, which is the horizontal axis, and the vertical axis is how many times, that's the count, this happens. We can see here is the horizontal axis goes all the way to 10 to the 9, which is a gigabyte a second. And so that's what the headline says, the transfer rate could reach 1 gigabyte per second to tape. That's very respectable. I presume actually that high speed actually is going to the disk cache on the HPSS system, not to the tape itself. But the measured rate actually can reach a gigabyte a second. The typical rate, the medium rate is 17.9. That's what rounded up to be 20 megabyte per second. That's the typical. And for those who are interested in a bit more pedantic numbers, like what's the difference between mean and median and mean? And mean because you're averaging with all those really high rate, like a gigabyte per second. So you end up with the mean value to be almost 3.5 times as high as the median value. That means there are lots of slow transfers, but because they're slow, they get averaged to be relatively large. Okay. So the average rate is quite respectable, even though there are lots of slow file transfers. So if you see there is a peak at 10 to the 5th, so that's less than a megabyte a second. It's 1/10 of a megabyte a second. So it could be fast or slow, but the average is very respectable of 76 megabyte per second. So one thing we were kind of curious is how does that rate change over time? And here are a few days where you have a significant amount of accesses to tape. And what we see is there are a couple of days, it seems that for the whole day, the transfer rates are low. So the natural question is, how come? Why are they so low? Can we look at the statistics and get some hint as to what is going on. Okay, so what I'm going to do next is to show you a few boxing plot. This boxing plot shows, okay, let's just take this May 15th as an example. The black bar here is it's the mean, and the widest box that's within one standard deviation away from the mean. And you can see on this particular day, there are a few slow ones and a few really fast ones, but the majority are around 30. So the majority of transfer is 0.3 times e to the 9, which is 300 megabytes per second. So that's actually quite high. And so what we see here is there are 2 days, the May 14th and September 18th. On those whole days, there's only one single transfer. So you get the average to be very low. But this is not always the case, because on September 27th, you get a single transfer, but that transfer is relatively fast. On the other 4 slow days we saw in the previous screen, and what we see here is, for example, if you look at the May 17th, what we have is, on average, there is a lot of relatively slow file transfers, a couple of outliers that is very slow, but there are also a few outliers that are particularly high. So we will need additional data to understand what is going on here, and the Dcache log itself does not record information like what else is going on the HPSS system, or what else is going on the network, right? So we need additional information to understand what is going on. There's another set of unusual features if we just follow a single file and look at operations on that file. What we see is, in most of the cases, this particular file is on disk, but there are a couple of weird situations that on September 12th, this red dot here, that file is retrieved from tape once. And on September 26th, this particular file is retrieved from the tape system twice. Though you can easily ask, what's going on? Did we miss something in the record? And why is it being retrieved multiple times? So this apparently is not a unique situation, and here are shots of 2 different files that goes through this similar access patterns. So if you are familiar with this type of files, you might know that this particular file ends with .root.1. That is a typical data file, while this file ends with .root.1.csv, potentially something different, and we would need to get more information to see what is going on. And the unusual thing here is there are in quite a few days, we got more than hundreds of accesses, repeated retrieval from tape. So something weird is going on, but we don't know why. So that's some of those statistics we were playing with. Here's a quick summary. So on an average day, there are about 3.5 million file accesses to about 1 million unique files. And most of those files are on disk. Like I said, only about 1 in 50 file accesses needs to go to HPSS, which translates to about 98% cache hit rate. This is very good for for a caching system. For the cache misses, about 70% of the files that are retrieved from HPSS are used multiple times, which means even though we only got 2% cache misses, there is still potentially room to improve the cache hit rate, especially because there seems to be disk space left unused, right? I mentioned during this 15-month period, we accessed about 5 petabytes of file, while there are 15 petabytes of disk space. So potentially, if we can make use of those 10 extra petabytes of space that are laying around, we might be able to reduce this cache miss rate even further. We need additional information in order to understand. I mentioned, there are multiple rereads from the tape, what's going on, and also on some of the days the file transfers are lower than other days, and what is going on there. So we're talking to the operators of Dcache system and the computer center folks to see whether there are easy ways for us to get access to those information and to further understand this. But overall, because the cache hit is working quite well, it's hard to convince them, this is the urgent need they have to address. So we are planning to do additional investigation. I mentioned group of files, data sets. For the physicists who are overseeing the system, they're interested in larger scale operations, not operations on individual files. They are more interested in operations on data sets and whether we can predict data sets, whether it's hard code or Wang and so forth. So we are getting more data from them, but they are pushing us to go to the direction of going beyond individual files, explore those data sets rather than individual files. And the other thing is there are multiple Dcache installations, and we are interested in looking at other Dcache installations. For example, the Nordic Data Grid facility that has their own Dcache installations, and how we might help them to operate their Dcache system better. So that's my prepared presentation, and I want to acknowledge the funding from Office of Advanced Scientific Computing Research, and thank everyone for listening. I'll be happy to answer your questions.
Well, actually, I've got a question for you.
Yes, go ahead.
So, it's about the multiple readings from tape. And did you investigate if this is due to poor concurrency in the Dcache system? So say that Dcache allows no more than 1,000 users simultaneously, then every other user will go straight to the tape. Those users which are not handled by owing to concurrency by Dcache will go straight to the tape. This may also explain why you don't see any intervening delete or remove message.
That's potentially possible, but I don't know specifics on this particular setup. Maybe Alex, do you have any information on this?
No, I don't have any.
Yeah, so potentially this is we want to talk to them, but like I said, they're not terribly interested in this particular problem seems like they're okay with this a little bit.
I was actually asking because that was what happened to me with a different caching system more than 20 years ago. It was a cache system for web servers. And once the maximum number of allowed users concurrently was reached, the cache was not in use actually.
I see. Well, we'll bring this up with them and see if we can get some answers on this. Because presumably that if that's the case, then there's a easy fix, right? Just ask them to bump up the limit.
Yeah, it may not be easy. It depends on how many users you want to concurrently support. Because say you need to spawn at least one thread per user. So this may impose a very high burden on physical resources.
Well, they might be willing to put in a bit more resources to it because they are serving everyone in the US. Well, I guess they can't really control it. If there's someone coming from outside, they can't exclude them. But you know, they're meant to set up to support thousands of high energy physicists. So they do have the resource to do something.
Okay, thank you.
Thanks. This is an interesting possibility we should investigate.
Hey, great presentation and interesting questions and answers. Any other questions? Okay.